Welcome. In the last video, I talked about how security engineers craft security stories and some tweaks to dynamic languages that might make it easier to enforce some important security stories. I'm going to apply those ideas to each of the puzzlers. I want to make sure that simple developer mistakes don't compromise security. Even though there were probably small tweaks to each of the puzzles that prevent the attack, I've argued that we shouldn't put the burden of avoiding these security problems on developers and code reviewers. They shouldn't have to know which subtly different way of expressing an idea is secure and which isn't. Here's our first puzzle. There's a link to puzzle 1 in the video notes below if you need a refresher or haven't worked through the problem yet. The immediate problem was that simple string inputs can cause arbitrary code execution. By calling capital of with unusual inputs, we can exploit metadata properties of the objects that implement the lookup table and execute arbitrary code. The more general problem is that properties like constructor that are about language elements are mixed up with properties about application elements, like facts about Alabama, and attackers can exploit those metaproperties. There's no way to separate user-defined properties from built-in metaproperties without fundamentally changing the language. Most of the danger from built-in metaproperties is unintended code loading, though. JavaScript engines have hooks that turn off this behavior. Content security policy turns off eval and capital F function. Here you can see a policy that allows two scripts. And here's our capital F code. The second script calls capital F twice. The first time it asks for the capital of Alabama in 1900. The second is the attack. If we look at this in the console, you can see that the first call worked and the second call failed. It refused to evaluate a string as JavaScript because unsafe eval is not an allowed source. This addresses the immediate problem. It's less than ideal because there are legitimate uses for big F function. Node.js introduced the same API under a different name, vm.runInThisContext. Tricking code into calling runInThisContext might be harder, but it suffers from the same flaw. It takes a string and runs it regardless of whether the string is trustworthy. As in the third puzzle, the decision to trust the string, implicit in passing it to run in this context, may be out of sync with the code that controls the string's content. When I discuss the third puzzler, it'll become clear how allowing a trusted script type's value to be evaluated, but not arbitrary strings, would address this in a comprehensive way, and how that would tie into strong security stories about code that is allowed to create trusted script values. Let's move on to our second puzzler. Again, there's a link to the original video in the notes. The underlying problem was that you can quickly write code that is mostly correct by manipulating bags of properties, but minor errors can lead to leaks and data overrides. Here's our security story. Only resetlinks.js can allocate password reset URLs, and they are unguessable. The URLs are boxed, and the box can only be opened by sendResetEmail.js. Only those modules could leak a reset URL, and careful review concluded that they do not. Therefore, leaks of reset links will not happen before the link is enqueued in email. The original code was a single module so that it fit into a code pen, but I've split it up. You can see that reset links and send reset email cooperate. This is our secure kernel responsible for managing password resets. This security story works because we've identified a small amount of code that needs access to reset URLs. We then check that those aren't leaky. To make this story true, though, I need some way to prevent any other code from accidentally leaking reset URLs. Here's a diff. The red code that starts with minus is the original, and the green code that starts with plus has the fix. Here, the reset link module boxes the unguessable URL. A box is a value that holds another value. Only an approved opener can access its content, so accidentally passing a box to a logger won't leak anything. The top change imports another module's public key, which is how it specifies whom to trust. I'll explain what a module key is in a bit. Here I've changed the email sender to unbox the reset link. This is running after being transpiled to add a polyfill to each module. Each module now has a public identifier, a private identifier, and a frenemies object with these box and unbox methods. The public key returns true when called in the context of the private key. This means that one module can't use another module's public key to impersonate it. And here's what unbox does. It stores the value in a weak map, so it is never reachable by reading a box's properties or calling its methods. Then unbox checks that the opener may open the box, and that the opener wants content from the box creator. So if I run the original code in Node, you can see that it leaks the reset URL down here. But if I run the new code, you can see that the URL property is still there. We didn't fix the surface bug. Remember, my goal is to make this code secure despite bugs. I made some very small changes in just 2 places to add a box and an unbox call and fix the problem. No matter what the rest of the code does, URL won't leak. I suggested in the wrap-up to the second puzzle using symbols as keys for sensitive properties. That addressed the immediate problem. This approach gets to the core of the issue. Symbols were originally proposed as a way to enable private fields, but they morphed into a namespace separation mechanism. Any security story that relies on symbols has to say something like, no object containing the reset URL reaches a stringifier that stringifies symbol properties. In my experience, that's a much harder security story to check or enforce, since it requires reasoning about the code in all modules, including your dependencies. For example, this JSON replacer goes out of its way to make sure it doesn't miss any properties using object.getOwnProperty symbols. There have been similar problems in Java where stringifiers used setAccessible to access private fields and methods. If you have a way to make that story work, though, please leave me a comment. There is also an excellent private properties proposal that will probably become part of the language, but it will not address this problem. Private properties help keep implementation details close. They do not prevent leaks of sensitive values that need to pass from one module to another, possibly through yet more modules. Opaque boxes do, though. There is a related mechanism in the computer security literature called sealer-unsealer pairs. This is a similar idea, but focused on providing secure channels between modules. This is not a data flow approach. Data flow schemes like COWL might address leakage more comprehensively. This scheme could complement dynamic data flow analysis, though. Public-private key pairs don't have to only correspond to modules. This scheme could bridge with a data flow scheme if there were a key pair per label. The third puzzle dealt with HTML. Again, see the notes below for a link if you haven't worked through it yet. Some HTML template code had a subtle bug. It assumed that only one primitive input value corresponded to a key in a table. I don't want security to depend on developers consistently avoiding these kinds of bugs, especially when that includes developers working under time pressure on code written long ago by someone else. So here's a security story that works. Our HTML templates have been reviewed so that the distinction between contributed content and site content is clear to users. The HTML template tag only lets trusted HTML values specify markup elements. Other values can only specify HTML text nodes. Only modules on the trusted HTML producer list can create trusted HTML values. All such modules have been carefully reviewed. Here we see 3 security story elements. There's a list of carefully reviewed files that lives alongside the source code, a restriction on which code can create trusted HTML values, and a security decision that grants special privileges to those values. Let's look at how we enforce those dynamically. Here's how we define the trusted HTML producer whitelist from our security story. You can see that create trusted maps to a set of files that should be allowed to import it. I hacked the module loader. When one module imports another, it calls this hook. If I want to prevent an import, I can substitute a different URL. This hook takes a base URL, the importing module, and the module to be imported. Then it returns the URL to actually load. In this case, it just allows loading of the module that was requested. In this case, it substitutes a different one based on an established naming convention. I won't go into the rest of this script in detail. It's not long, just dense. The important thing here is that we have a way to declare which modules are sensitive and which modules need to import them anyway, and then to enforce that. Because of some specific design decisions, I can run this policy before any ES6 modules are loaded. Here's a Babel plugin that checks imports. These intercept hooks don't complicate code bundling. First, We abstract away the URL space. Then we use Babel to apply the policy and rewrite import declarations. Here's where we apply the policy, and here is where we substitute a fixed URL. So we looked at how import hooks work. Let's see how our security story affects the way we rewrite code. If escape HTML's input looks like a trusted string of HTML, it unwraps it instead of escaping it. Strip tags does the same. And here's our new HTML template tag definition. The diff doesn't fit on one slide. The bolded if body was rewritten. Now it only uses the double $ queue to decide which escaper to use. It lets the escaper decide how much escaping is done, and those escape functions only grant privilege to inputs that are marked trusted. An attacker would have to full code on the whitelist if they want to get a privileged value with payload here. That's a much smaller target. Here's trustedtypes.js. This is library code that's based on the proposed trusted types standard. It represents trusted strings of content, like HTML, JavaScript, CSS. The trusted HTML class just wraps the box to make it JavaScripty. Function unwrap unboxes an instance, but it also checks that the box came from createTrusted. This enforces the only trusted HTML values part of our security story. At the bottom, we attach unwrap to trusted HTML as a static method. Here's createTrusted.js. It exports a function that creates a trusted HTML string. Our security story says that only certain code creates these values, so this is the module that our whitelist guards. If you're interested in this pattern, see the link in the notes to the trusted type standard proposal. We use libraries like it extensively within Google to provide security by construction for strings of code. The exported function simply boxes the HTML string along with the type indicator. Any module can open it. Our legacy names table now stores trusted HTML values. This module is on the whitelist, so can import createTrusted. The reviewer noted that it's safe because it is only called with constant strings. Our use of the HTML template got simpler. Instead of calling isLegacyUser, it just passes the value straight through. Even if it did still have those checks, it would neither over nor under escape, since the decision to escape is based on whether the value has a trusted type. Here's what we get when we try our attack. Here's the payload. Strip tags runs over that payload, and what you get is an innocuous result. I didn't set out to fix the bug, but by virtue of marking things as safe where we know that they're safe, that buggy code became irrelevant. I hope I've convinced you that there are a few changes to JavaScript that will give security engineers the tools to craft strong security stories that do not depend on the correctness of the majority of code. We can remove the burden of guaranteeing many interesting security properties from developers and have more productive relationships between developers and reviewers. Here's the argument in a nutshell. I asserted based on the first puzzle that we can't rely on developers, reviewers, and unsound linters to catch common security problems. We need ways to preserve security even when code written in good faith has errors. We can't efficiently deploy human judgment to check security stories that assert about all code, but we can for only code. The proposed mechanisms make it practical to enforce a wide variety of only code stories with small targeted code changes. Adding these mechanisms to web infrastructure will make important security stories feasible. Finally, I've tried to avoid security and programming language jargon in this series, but I'd like to try to anticipate one objection from other security folk. Some have argued that Spectre makes approaches like this obsolete. Some respected researchers have even said that language-based security is dead, and that we shouldn't waste time on any isolation mechanism less thoroughly hardened than process boundaries. A Spectre-based exploit could break the security story for the second puzzle, since the password reset link is stored in memory. It does not affect the other two, though, since Spectre by itself does not affect integrity or availability unless those depend on confidentiality. The mechanisms I propose do not depend on confidentiality. There is no secret that lets you forge a module identity, since they depend on reference identity. You would have to have a memory write compromise in a JavaScript engine process, in addition to a read compromise. That an integrity violation in a JavaScript engine can compromise the security of application JavaScript is not a surprise, nor is it a defeater for my claim that we can improve the security of application-level JavaScript when integrity and availability do not depend on confidentiality. Anyway, enough of that. Thanks much for watching, and I look forward to engaging with you in the comments or on Twitter.